This video presents collaborative exploration with a Marsupial ground area robot team through task-driven map compression. Efficient exploration of unknown environments is crucial for autonomous robots, especially in confined or large-scale scenarios with limited communication. We propose a collaborative exploration framework for a Marsupial ground area robot team that leverages the complementary capabilities of both robots. The framework utilizes graph-based path planning to guide exploration and to trigger the deployment of the aerial robot in regions where its expected exploration gain exceeds that of the ground robot, thereby maximizing overall coverage and efficiency. To facilitate large-scale spatial information sharing, we introduce a bandwidth-efficient, task-driven map compression solution. Our approach focuses on achieving a high degree of compression while enabling the reconstruction of volumetric information at a specified voxel resolution rather than the raw point clouds. This process inherently filters out spatially significant fine details through voxelization, minimizing their impact on compression efficiency and achieving strong occupancy similarity. In the simulation, the robot team is assigned the task of exploring a multi-level building with interconnected rooms, hallways, stairs, and ramps. The mission begins at the Marsupial starting point with the ground robot carrying the aerial robot in a Marsupial configuration. As the ground platform explores the environment using a graph-based path planning algorithm, it stores keyframes consisting of compressed point clouds and their corresponding sensor poses. Simultaneously, the ground robot simulates the aerial robot's graph to determine when deployment is necessary. In this study, the aerial robot is deployed when the ground robot encounters inaccessible areas such as staircases. At that point, the ground robot shares a subset of the stored keyframes along with the aerial robot's target location. The mission then continues with both robots exploring independently and exchanging maps whenever they are within communication range. The effectiveness of the data sharing is highlighted by two key moments, referred to as pivot points. When the aerial robot autonomously repositions itself to unexplored areas after recognizing that its current area had already been mapped by the ground robot. Both robots return to the initial deployment point when a regrouping is triggered. The mission concludes once all previously unshared information has been exchanged. To demonstrate the applicability of the proposed framework, we conducted a real-world experiment in a multi-story university building featuring hallways and open spaces. The Marsupial robot team, consisting of a legged ground robot and an aerial robot, began exploring the unknown environment. The ground robot continued its exploration until it identified a deployment point where a physical obstacle blocked further progress. At this point, a colocalization process was performed to align both robots within a common inertial frame, allowing them to operate within a unified map. The ground robot also shared the compressed map data and the aerial robot's target location. Following deployment, both robots explored independently on different building floors and returned to the deployment point when regrouping was triggered. The mission concluded once all previously unshared information had been exchanged.